But angular momentum for a little while, and I wanted to take a second to just sort of summarize and connect some ideas before we start to move on to asking the question, how does angular momentum change? So one of the sort of things I wanted to connect was this idea that we actually have talked about angular momentum for a lot of different types of situations. For example, we've talked about the angular momentum of an individual particle moving, right? And for an individual particle, the angular momentum of the particle is simply the position vector of the particle crossed with the momentum of the particle. And so just like it's possible to have some object moving along in a straight line and to have it be sensible to talk about that object having an angular velocity, because an observer sitting at the origin sees the angle change, it makes equally good sense to talk about that object that's moving in a straight line having an angular momentum, right? Each point has, in fact, a position vector associated with it. At each point in time, the particle has a momentum that's to the right, and in this particular case, if I took r crossed into p, I would find an angular momentum that was into the page. So I can have an angular momentum for a particle. I can also have angular momentum that's due to pure rotation, right? So if I have some body that is rotating, like a turntable or a wheel that's rotating about its center, right? So I've got omega coming out of the page. Then it makes sense for this case to also talk about the angular momentum as simply being proportional to what the angular velocity is, and that constant of proportionality is the moment of inertia. Now, we got to this moment of inertia by actually thinking about what the angular momentum of an arbitrary system is, and that is an extension of this idea for a particle. So if the angular momentum of a particle is r cross p, the angular momentum of an arbitrary system is a sum over all of the particles in the system of the position vectors of those particles crossed with the momentum of those particles. And if you actually follow this argument through for this case of a rotating body, you end up finding out that you can write the angular momentum simply as the angular velocity times the moment of inertia. And finally, we've talked about angular momentum for a system that is both rotating and translating, and this is where we introduce this idea that you can break angular momentum down into the angular momentum that is of the center of mass, right? So the angular momentum that is due to sort of taking the object, compressing it to a particle, and asking how the particle is moving. And then you add to that the angular momentum about the center of mass. So that you sort of break angular momentum down into a translational component, which sort of corresponds to a particle abstraction, and then a rotational component that's sort of expanding that particle abstraction into a rigid body that's not just translating, but also rotating. And so there are a number of different expressions here, but they all come from this sort of core idea that for an arbitrary system, you can write the angular momentum by thinking about each particle in the system and asking questions about what the momentum of each particle in that system is. Okay? You'll note just from a units perspective, right? Momentum has units of kilogram meters per second. Position has units of meters, so the units of angular momentum had better be kilograms meters squared per second. And you'll also note that angular momentum, that when you do that, you can see what the moment of inertia units are, which you can also find by looking at how you calculate moment of inertia. Right, moment of inertia is simply kilograms times meters squared, which you of course can see here. Angular momentum has units of radians per second. Radians are dimensionless, so you pick up the per second from the omega, and moment of inertia is kilogram meters per squared. So I wanted to make those comments about units before we go on to talking about torque, and in the next video we'll talk about torque.